I'm going to be working on filling in our notes and examples for the part 1 of the final review covering chapter 1 and chapter 2 information. Feel free, of course, to skip 2 parts that you need based on what you missed in class. So to start with, I'm going to start in 1.1, and the important note to take note of is the definition of a function. The definition of a function for each input or x value corresponds to 1 and only 1 y value or output. Okay. Example 2, just taking a look at that graph, being able to read the graph in order to give g of -2, as well as give the domain and range. Of course, we will have to give the domain of a function given the equation, but we'll cover that later on in the review. So g of -2, we go to -2 and we come up, the empty point there makes us go up to this point, so g of -2 is 3. The domain is from -4 through 5. We don't have to worry about that point where this is open because it is defined here, so there is an output there. And the range is from -2 to 3. On to the 1.2 and 1.3 information, which covers our sequences. In 1.2, I expect you to be able to take a recursive formula or any formula and get terms of a sequence from it, and then be able to graph. So as the example here, I have u sub 1 equals 2. I have to find the first 5 terms. I'm already 1 in. So then I need to find 4 more terms. So to get the second term, that would mean u sub 2, which is equal to 3 plus u sub 2 minus 1, which is 1. And therefore, that is 3 plus -2, which is 1. We can continue down that route for each term value. However, we can also say that this notation means to get one term, we add 3 to the 1 before it. So therefore, I can say I have -2, 1, and then I'm just going to keep adding 3. I have 1, 2, 3, 4, 5 terms, and that's it. We also have to be able to graph sequences. I'm going to steal space over here to be able to graph. I did this by changing my scale to 2's just to make it fit in this little space that we're looking at. The u sub n value goes on the y-axis, the dependent. The n value is the independent. And so when I go to graph, the first term is at -2. The second term was 1. Third term is 4. Fourth term is 7. And fifth term is 10. And we don't connect because there's no in-between terms. That is it. It's a discrete graph. Moving on, 1.3, we covered arithmetic sequences. Arithmetic sequences are a type of sequence where we repeatedly add the same thing to get from one term to the next. So therefore, the recursive formula looks like this. We'll say what u sub 1 is equal to, and then we say u sub n is equal to the previous term plus that common difference, that thing that we're adding. An explicit formula, u sub 1 is equal to n minus 1 times d plus u sub 1. And I usually rearrange that. I don't know why I just wrote it that way, but it's the same thing. And again, that is giving us, the explicit formula tells us how to get, this is u sub n, sorry, how to get to any term in a sequence. And all you have to know is the common difference in the first term versus in the recursive formula. We have to find every term prior to the one that we're looking for. And in both of these cases, d is the common difference, meaning that is the value that is added between each term. Summation notation, we also have to be able to do that. So we have to be able to plug the n values from 1 through 6 into here, and then we'll find the sum of when that happens. Again, another part of this section was we did something called partial sums, and we had a formula for that, and that was something that we would use like if we wanted to find the sum of the first like 200 terms. So I've said that that will not be included on the final. So therefore you don't have to worry about that formula or how to use that formula. And one more here. 2 times 6 minus 3. Okay, so I plugged all the n values from 1 through 6 in, and then I have to add each of those together. Again, that's what the summation notation means. That gives us 24. Again, this is a really quick and brief overview, just to kind of get your minds thinking about this and have important pointers referencing this material. This is not all of what you should be doing to review for the final. It's just a starting point. All right, moving on to 1-6. 1-6 is when we worked with geometric sequences. Geometric sequences are a type of sequence where we keep multiplying with the same value to get from one term to the next. That thing we multiply by is the common ratio. So our recursive formula for a geometric sequence, we give the use of one value, and to get a term, we multiply the previous term times the common ratio. The explicit formula to get any term in a sequence, we repeatedly multiply by r, so it's r to the n minus 1 times u sub 1 to get from the starting point and get to any other term. Okay? You have to be able to both write those formulas and use those formulas. In 1-5, we worked with lines, linear equations, and functions. So slope formula, how do you find slope? So this is slope formula, not necessarily slope intercept. Point slope is what we use a lot of times to write the formula or write the equation of a line. Y minus y1 equals m times x minus x1. Sorry, in the slope formula, it's change in y over change in x. Slopes of parallel lines. Parallel lines have equal slope. And perpendicular lines have slopes that are opposite reciprocals. So for example, if I talk about 2, the opposite reciprocal of that, I flip it is 1/2, and then change the sign so it's negative 1/2. Okay, and working with so in 1-5 we did specifically linear models. So how do we do that on the calculator? So we would go to Stat and select Edit. L1 is where we put the independent variable, or the x value, sorry, independent. L2 is where we put the dependent, the y. We then go back and we hit Stat again, and we would choose Calc, and in this case we would choose linreg. Another quick note, especially if anybody has done anything new or different on your calculator, make sure your diagnostic is on if you want to see the R value. Diagnostic on to give the R value, that's under the catalog. Or you can always Google it. How do I turn my diagnostic on my graphing calculator? Again, we also did modeling of other forms later on in the year. So this kind of gets tied in with that same information. We talked also about residuals in 1-5. I'm just doing the linear modeling. You don't have to worry about being able to talk about residuals. All right, in chapter 2, we talked about solving equations, solving inequalities, solving funky equations, solving using a graphing calculator is what we did in 2.1. So we did things like if I have an equation, set one side as y1, the other side is y2, and we find where they intersect. Or you can move everything to the other side of the equation and find where they cross the x-axis. Either model is, or either form you can use. However, we did have a couple different types of functions that had weird graphs sometimes. And that was if we had the square root of f of x, so we had like some kind of polynomial under the square root and we wanted to find when that was equal to 0. You can, if you need to, you don't always have to do this, you can, instead of plugging this whole thing into the calculator, instead you can just solve f of x equals 0. Because the only way for the square root of f of x to be 0 is if f of x is 0 itself. Ditto for a rational expression. If I have f of x over g of x equals 0, again, I can solve just f of x equals 0, but then you need to check your answers and g of x. Okay. Again, that's because this fraction, the only way for it to be equal to 0 is for the top to be equal to 0. However, we also can't, that if it also makes the denominator 0, then it's actually undefined there and it's not a solution. Okay. All right, quadratics and 2.2, we solved quadratics using square roots, factoring, and quadratic formula. We have to be able to give simplified exact answers as well as approximate answers. Quadratic formula, somehow some of us don't remember it. Too much other stuff in your brain. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a. We also talked about the discriminant in this section. Don't have to worry about that on the final. In 2.2, we also, sorry, it's a continuation. It was mostly quadratics, but we also took the factoring and applied it to solving these type of quartics. So a quartic that we could solve like this, we could make it 4x squared minus 3 times 4x squared minus 1 equals 0. The other thing that we did is I showed you also about how to use u equal x squared. That's the other method that we learned in that section. To continue this, not 4x squared, just x squared. Sorry, everybody. So then this would be x squared equals 3, so x equals plus or minus root 3. Sorry, it has to be 1x squared times 4x squared to get 4x squared. Otherwise, we'd have 16x squared the way I had it, and none of the rest of it would work either. All right, and then 4x squared minus 1 equals 0 leaves us with x squared equals 1/4. We take the square root and we get x equals plus or minus 1/2. Quartic, fourth degree, has 4 possible real solutions. All right. In 2.3, we talked about application problems. Application problems that we talked about, there was a wide variety. We had rate problems, geometry problems, and what have you. However, I've kept it only to the mixture problems. So in our example here, if you read through it, we have a set amount of money that we're investing or that Chris is investing. He gets 2% on the portion that he puts into one account, and he gets a 5% rate of return on a portion he puts in another account. If after a certain amount of times he netted 3.4%, so that's 0.034 of his entire investment, so that was $550. And we want to know how much should he invest in each place. In order to solve this equation, I have two unknowns. If I have two unknowns, I actually need two equations. So our other equation is just the fact that the total amount we invested, so the amount that went into the low risk stock and the amount that went to the high risk stock, was $550. We would then set that up and solve that as a system of equations. So you could use substitution. You could use elimination if you wanted to. I would definitely do substitution. Okay, moving on in 2.4, we talked about a few different types of equations to solve, and also we had situations where we had to check our solutions. For our first example here, our absolute value, we have to consider both the positive, and then we also have to consider when we have a negative, or a number on the other side, we have to say positive and negative. When we have an expression, we have to consider that expression, or it could also be equal to the opposite of that expression. And then solve. And if I go through my work to solve here, on this one I'd get x equals 4/3. And over here I'd get x plus 3 equals, make sure you distribute that negative throughout, negative 4x plus 1. And working on solving there, I'd get x equals negative 2/5. You then have to check your solutions. Anytime in an absolute value or the radicals or these rationals, you have to check solutions. So going back and checking, absolute value, you only really have to check if it's a variable expression on the other side, because we have to make sure that a negative number isn't on the other side, because if we take the absolute value of something, it has to be positive. Okay, so plugging in, if I take 4 times 4/3, and I actually only start over here on this side, 4 times 4/3 minus 1, that will not get me a negative answer, so all is well. If I plug in negative 2/5, however, I get the absolute value of negative 2/5 plus 3 is equal to 4 times negative 2/5 minus 1. I could crunch numbers. 4 times negative 2/5, it's going to give me a decimal, negative 1.6, but I also know it's negative 1.6 minus 1. This is a negative number. I cannot take the absolute value of something and get a negative number as the result. This guy is scratched. It's called an extraneous solution. Okay. In the next one, working with these radicals, I have to isolate the radical in order to then square both sides to get rid of that radical. Radical of different powers we use. If you had a third root, you'd have to raise everything to the third power. This is a square root, so I'm raising everything to the second power. So I get 4x plus 33 is equal to 4x squared minus 4x plus 1. Again, remember that this means 2x minus 1 times 2x minus 1. Don't call that just 4x minus 1. We have a whole middle term there to remember. Rearranging, I'll get 0 equals 4x squared minus 8x minus 32. Nice enough. Everything is divisible by 4. Since I have an equation, I'm allowed to divide by 4. If you don't have an equation, you can't lose that 4. It'd have to stay out there. But in this case, I can just say I'm dividing everything through by 4. So I get 0 equals x squared minus 2x minus 8. I factor and solve. 0 equals x minus 4 times x plus 2. So I get x equals 4 or x equals negative 2. Again, I have to check my answers with these. So in this case, if I plug in 4, I get 4 times 4 is 16. 16 plus 33 is 49. Square root of 49 is 7. 7 plus 1 is 8. We're good. And 2 times 4 is 8. I'm just going through talking it through because that's a good answer. The one that doesn't work is negative 2. If I take 1 plus square root of 4 times negative 2 plus 33, can that equal 2 times negative 2? I end up over here. That is the square root of 25, which is 5. And it's not plus or minus 5 in this case. You're not solving. You're just taking the square root of 5. So it's 1 plus 5. Does that equal negative 4? So therefore that one is scratched. In all of the examples I'm doing right now, I'm coming up with extraneous solutions because I just want to show you those possibilities. There are a lot of times actually when we didn't get these extraneous solutions. All right, moving on to 2-4. Similar to what we talked about in the 2-1 example, the only way for a fraction to be equal to 0 is if the top is equal to the 0 but the bottom is not. So therefore I solve for when the top is equal to 0, and then I check that that same number doesn't make the denominator 0. So factoring and solving, 2x plus 3 times x minus 1 equals 0, x equals negative 3 halves, and x equals 1. So again, before I box, I have to check. And I check in the bottom, I have to make sure, because if I have a 0 on the bottom, that's undefined and it can't be a solution. If I check x equals negative 3 halves in the bottom, and only in bottom, I get 2 times negative 3 halves squared plus 5 times negative 3 halves plus 3. Beep boop 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 on the calculator, and that actually, oh sorry, that's a, yeah, 5. Yes, beep boop 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 on the calculator, and this comes out to be 0. So this is not a solution. Sorry, no, not a solution. X equals 1. If I check that in the bottom, it's 2 times 1 squared plus 5 times 1 plus 3. That does not equal 0, so I keep it. Okay. Again, going back over to here, very similar when we talked about if I have a rational expression that I'm solving on the calculator. The reason why in this case that we could just plug the top in is it's a little bit easier than plugging in the whole equation, and it makes it a little bit of an easier graph to work with. Okay, versus over here, it's really the only way to solve what we're doing is by just making the top equal to 0. Okay. All right, one more example for part 1. Solving that we did linear inequalities and quadratic inequalities, and also we did linear compound inequalities. So taking a look just at this quadratic inequality. Again, going back to in this chapter, in this section, the temptation is to solve this just like a linear equality. Factor this, say it's less than or equal to 0, set each of the factors less than or equal to 0. However, that doesn't work because of the shape and the nature of a quadratic. So instead, I think of this for a minute as an equal sign. I have to find what makes it equal to 0. So I'm going to say x squared plus 9x plus 18 equals 0. I'm not changing it to an equation, I'm just finding what the zeros are first. X plus 6 times x plus 3 equals 0, so x equals negative 6, x equals negative 3. If I think of the graph of this guy, so I've found that it crosses at negative 3 and at negative 6. A quadratic graph either opens up, it's the U shape that opens up, or it's a U shape that opens down. Since the A value is positive, then we can say this is a parabola that opens up. We are looking for when this parabola is less than or equal to 0. When is the parabola below the x-axis? That happens between negative 6 and negative 3. So my solution set is negative 6 to negative 3. I don't know what that was. As opposed to saying x less than or equal to negative 6 or x less than or equal to negative 3. That doesn't work with the quadratics because of the fact that they have that point of inflection and they turn and they change the direction they're going. Okay. The other way we talked about this, you could think of the shape of the graph, or the other thing I said was we also could do a test point. So again, calculus, you use the concept of a test point a lot. So you could say, okay, this is where the 0 was. Sorry, you wouldn't really draw the y-axis on there if you're doing this. -6 is a 0, and test a point between -3 and -6, like -4. It's easier if you plug it into the factored form. If you plug in -4 plus 6 times -4 plus 3, this is positive 2 times a -1, that gets you a -2. So again, it's just another way, it's just boiling it down to just the signs to see that that's when it's negative. You could then double check out here and see that these are the places where it's positive. And again, if we're looking for where it's less than or equal to 0, then we're looking for where it's below. So again, it depends on what this says, if you're looking for where it's below the x-axis or if it's above the x-axis. It also makes a difference if you're quadratic, your initial quadratic is opening up or down. Okay, so that is all the information and notes that were covered on the note sheet. Again, try the practice problems. We'll be talking about them tomorrow in class, and I'll be answering any questions that you have about them. Have fun!